Refraction of light through a prism. Before we investigate how light behaves in a triangular prism, let's think back to how light behaves when it enters a transparent slab of material which has parallel sides. The light enters from an optically rarer medium at a higher speed into an optically denser medium which has a lower speed of light. As a result, the ray of light bends towards the normal. Then, as the same ray emerges on the other side of the slab, it is emerging from a denser medium into a rarer medium, so the ray again bends away from the normal. If you look at the diagram, you can see that the ray is not really bent as much as it is shifted laterally. A prism differs in this matter because in a prism, the other faces are not parallel to each other. We shall be considering a very specific type of prism in which the faces meet at the same angle, that is 60 degrees. In other words, the side of this prism looks like an equilateral triangle. The incident ray is hitting the first surface at an angle. Please remember, all angles are being measured with respect to the normal because the normal is always perpendicular to the concerned face. The incident ray makes an angle I with the normal. Since it is entering from free space which has a lower refractive index into glass which has a higher refractive index, the ray will bend towards the local normal. In this particular case, the ray is exactly parallel to the bottom face of the prism. Now, on the other side, the same ray will now emerge into the free space or the air medium again. Now, it is proceeding from a medium of high refractive index into a medium of low refractive index. So, in this case, the emergent light or the emergent beam will bend away from the normal at angle E. So, while a rectangular slab with parallel sides causes a lateral shift in the ray of light, a triangular prism will instead bend the light at an angle to the angle made by the incident ray. Dispersion of white light by a glass prism. You may have noticed a very beautiful and interesting phenomena when you look at a rainbow or when you look at the pattern of light cast by falling droplets in your shower. You see that normally white light is being split into an array of beautiful colors. This phenomenon was investigated in detail by Sir Isaac Newton, and today it is known as the dispersion of light. Dispersion of light can be readily seen using a prism, as we discussed earlier. If we take a beam of white light and allow it to enter a prism, we notice that we get a multicolored set of beams on the other side. If you look at the order of the colors in this multicolored beam, we seem to see an order that is always the same no matter where we get the light from. It follows the order violet, indigo, blue, green, yellow, orange and red. You will observe the same order no matter what type of white light you use. The intensity of the color may vary, but the reason you always see the same sequence of colors is because the wavelengths of each type of light is different. Light of red color has a large wavelength and is bent the least. It suffers the least refraction. While violet light, which has the shortest wavelength, gets refracted the most. That is why you see the least deviated color red towards the top and the most deviated color violet towards the bottom. Another example of dispersion that we see in nature is the rainbow. In the rainbow, things get slightly more complicated. Each individual raindrop is acting like a prism, and it shows both the phenomenon of total internal reflection, in which light bounces off the discontinuity or the boundary between the water and the air, and also shows dispersion like any regular prism. A large collection of these droplets, all dispersing the same white light, produce the beautiful display that we understand as the rainbow. Next topic, atmospheric refraction. Light comes to us from outer space. Outer space is a vacuum. However, the air medium has an effect on the incoming light. there is a small but measurable difference between the speed of light in a vacuum and the speed of light in air. As a result, light which enters the atmosphere from outer space gets bent, and this bending of light produces some rather interesting effects. One of those effects is the twinkling of stars. Stars are extremely small to us due to their huge distance from us. A star can be considered a point source of light, or it can be visualized as a single beam of light entering the atmosphere. Since the light is entering from an optically rare medium into an optically dense medium, meaning the speed of light in the atmosphere is less than the speed of light in a vacuum, the beam of light coming from the star will bend towards the normal. The normal is created at the interface of the atmosphere and the vacuum. As a result, the bending of this light will cause the image of the star that we see to be slightly above the actual position of the star. It is also important to note that the atmosphere of the Earth is not static, it is dynamic. It has turbulence, it has wind currents. All of these effects cause a shifting in the beam of light coming from the star, and it is this variation in the beam of light caused by the varying refraction of the atmosphere which causes the twinkling. But this presents an interesting question. We have seen planets like Venus and Mercury, and even though they are far away, they don't seem to twinkle. In fact, we learn this difference from an early age. Planets don't display twinkling. But then what is different here? The difference is that these planets are far closer to us compared to stars. And while the stars can be considered point sources, a planet is an extended source. Now, what does that mean? What is an extended source? A planet, instead of being a single point of light, can be considered as an extended collection of points spread out in space. Each of these points is sending a ray of light through the atmosphere into our eyes. Because all of these rays are varying by different extents, all these deviations average out to zero, and as a result, we do not see twinkling in planets. Another interesting effect caused by atmospheric refraction is the advance of the sunrise and the delay of sunsets. We observe that on Earth, we seem to see the sun rising a few minutes before it actually rises. This is because as the light comes towards the Earth from below the horizon, the atmosphere of the Earth is bending the light towards us. So we are able to see the sun even though technically it is below the visual horizon. At dusk, the opposite effect happens. Even though the sun has already receded below the horizon, the beams of light coming from it are still bent towards us, and we still see the sun even though technically it has already receded below the horizon. This is called the delay of sunset.